in the darkness between stars, where no planetary warmth has ever reached and no stellar wind has ever blown. A fragment of ice and stone continues its patient drift through the cosmic deep. This wanderer measures perhaps a kilometer across, small enough to rest comfortably within a city block, yet ancient enough to remember the formation of distant worlds. Its surface bears the accumulated dust of millions of years, a fine patina of cosmic debris that settled grain by grain as it traveled pathways no human eye has ever traced. The object moves in silence through regions where temperature hovers just above absolute zero, where even helium would freeze solid, if any existed here to freeze. Its nucleus contains water ice laid down when the galaxy was younger, when the stars that formed it still burned in configurations lost to time. Methane and carbon monoxide rest frozen within its core, molecular fossils from stellar nurseries that dissolved into darkness eons ago. Every atom in its structure tells a story of deep time. Hydrogen fused in the hearts of ancient suns. Heavier elements forged in supernovae that lit the void before our solar system ever condensed from its own primordial cloud. Scientists will eventually designate this visitor 3I/8less, marking it as the third confirmed interstellar object to pass through our solar system. The I stands for interstellar, a simple letter carrying the weight of vast distances and unimaginable journeys. Atlas refers to the ground-based telescope survey that will first detect its presence, though the object itself remains unaware of these future human designations. It simply continues its ancient trajectory, following gravitational currents that flow between the stars like invisible rivers. The comet's orbit traces a hyperbolic path, not the closed ellipse of solar system natives, but an open curve that speaks of origins elsewhere, somewhere in the galaxy's spiral arms, perhaps near a red dwarf star whose planets never knew complex chemistry, or in the outer regions of a system where gas giants swept clean the spaces between worlds. This fragment broke free from its birth family. The escape might have occurred gradually through the patient gravitational influence of passing stars, or suddenly in the violent disruption of a close stellar encounter. Either way, the result remains the same: a small world set adrift in the galactic ocean, carrying its frozen cargo across distances measured in light years. What strikes astronomers as remarkable is not the object's existence, the space between stars likely teems with such wanderers, but rather the rarity of detection. For every interstellar visitor that passes close enough to Earth's telescopes to reveal itself, countless others glide unseen through the outer reaches of the solar system. They arrive from random directions, following trajectories determined by encounters with stars whose names we will never know, carrying samples of planetary systems whose compositions remain forever mysterious. Only the tiniest fraction ever venture close enough to our sun to begin the subtle transformation from invisible wanderer to visible comet. This particular visitor approaches from the direction of the constellation Lynx, though its true origin lies far beyond any star visible to the naked eye. The gravitational influence of the Milky Way's spiral structure has nudged it across vast distances, each encounter with stellar gravitational fields adding tiny perturbations to its path. Gas clouds scattered throughout the galaxy have exerted their own gentle pressures, and the radiation pressure from distant quasars and active galactic nuclei has contributed microscopic course corrections over millions of years. The result of all these influences is a trajectory that will carry the object deep into our solar system's inner regions, close enough to the sun to awaken processes that have slept in its frozen nucleus since its formation. The comet's surface temperature currently hovers around 10 Kelvin, 10 degrees above the theoretical limit of absolute zero. At such temperatures, familiar materials behave in ways that seem almost magical. Water ice becomes harder than steel, while gases that define terrestrial atmospheres exist only as thin frosts coating the nucleus. Carbon dioxide, which bubbles vigorously from Earth's polar ice caps, lies dormant as solid crystals mixed with water ice in ratios determined by the chemical conditions present when the object first condensed. Methane, which flows as liquid on Saturn's moon Titan, remains locked in crystalline structures so stable they could persist for billions of years if left undisturbed. Yet disturbance approaches in the form of our star's gravity well, that invisible funnel in space-time that has been drawing the visitor inward for thousands of years. From the comet's perspective, the Sun remains just another star among many, brighter now than when the journey began, but still merely a point of light against the cosmic backdrop. The visitor has no awareness of the dramatic transformation awaiting it as solar radiation begins to penetrate the outer layers of its nucleus, stirring molecules that have remained motionless since the age of stellar formation. Astronomers understand that this approaching encounter represents something profoundly rare, a direct sample of interstellar material delivered to their instruments by the galaxy itself. Unlike meteorites, which originate within our solar system and carry the chemical signatures of our particular stellar neighborhood, this visitor bears the isotopic fingerprints of stellar processes that occurred in entirely different regions of the galaxy. Its deuterium ratios, the abundance of rare elements, and the molecular structures preserved in its ices will provide glimpses into stellar formation regions whose light has never reached Earth's telescopes. The mystery that will most intrigue researchers is the object's curious behavior during its closest approach to the Sun. Unlike typical comets, which respond predictably to solar heating with increasing activity and brightness. 3I/Atlas will demonstrate a puzzling restraint. At the very moment when solar energy should trigger the most dramatic outgassing and visible activity, the comet will instead enter what observers will describe as a strange pause, a period of unexpected calm that defies conventional understanding of cometary physics. This behavior suggests that interstellar objects may operate according to different rules than their solar system cousins, perhaps reflecting different formation conditions or compositional variations that remain invisible until subjected to our star's revealing heat. For now, in the deep, cold between worlds, the visitor continues its patient approach, carrying within its frozen heart the accumulated history of stellar generations. Each ice crystal preserves conditions from epochs when the galaxy's spiral arms occupied different configurations, when different populations of stars enriched the interstellar medium with their fusion products and their final explosive gifts. Soon, very soon in cosmic terms, the Sun's gravity will bend this ancient trajectory toward Perihelion, and the visitor will begin the transformation from invisible wanderer to active comet, revealing secrets that have traveled across light years to reach our waiting instruments. The gravitational whispers begin as barely perceptible tugs across distances that dwarf human comprehension. From 20,000 astronomical units away, 20,000 times the distance between Earth and Sun, our star's influence reaches out through the fabric of space-time like fingers trailing through still water. The visitor feels this pull as a gradual deviation from the straight-line path it has followed for millennia, its trajectory bending with mathematical precision toward the inner solar system. What astronomers will later calculate as a hyperbolic orbit begins its long, graceful curve toward perihelion. At such distances, the Sun appears as nothing more than a bright star among thousands, its light taking nearly 3 full days to cross the void between star and visitor. Yet even this faint radiance carries momentum, exerting radiation pressure measured in piconewtons, forces so gentle they could barely disturb a soap bubble, but persistent enough to influence the motion of objects across interstellar distances. The comet nucleus. Dark as charcoal and absorbing what little sunlight reaches it, begins an almost imperceptible warming that will continue for years as the approach progresses. The visitor travels at roughly 26 kilometers per second relative to the Sun, a velocity that speaks of its interstellar origins. Solar system objects, bound by our star's gravity since their formation, move with speeds determined by orbital mechanics and the Sun's mass. But this wanderer carries the signature of galactic rotation, of gravitational encounters with stars whose names exist only in astronomical catalogues, of passage through molecular clouds and stellar association regions scattered across hundreds of light years. Its speed reflects the cumulative influence of the galaxy's spiral structure, a velocity fingerprint that immediately identifies it as foreign to our solar system's native population. Deep within the comet's nucleus, where temperatures have remained constant for millions of years, ice crystals preserve molecular arrangements from stellar formation regions whose physics operated under conditions never replicated in our solar neighborhood. The water molecules locked in these crystalline structures carry isotopic ratios, the relative abundance of deuterium to ordinary hydrogen that reflect nucleosynthetic processes occurring in different stellar generations. Heavy water, with its extra neutron, forms in precise proportions that depend on the temperature and density conditions present when the ice originally condensed around dust grains in the interstellar medium, carbon monoxide ice. Invisible to casual observation but detectable through infrared spectroscopy, lies mixed with water in ratios that reveal the chemical conditions present in the visitor's birth region. This molecule, deadly to terrestrial life but common throughout the galaxy, serves as a thermometer preserving ancient temperatures. Its crystalline structure changes subtly with formation conditions, creating molecular fossils that encode information about stellar winds, shock waves from supernovae, and the gradual cooling of gas clouds as they condense into planetary systems. What remains puzzling to theoretical models is the visitor's apparent stability during its long interstellar journey. Cosmic rays, high-energy particles accelerated by magnetic fields around pulsars and active galactic nuclei, should have gradually altered the chemical composition of the surface layers, breaking apart complex molecules and creating radiation-processed materials unlike anything found in solar system objects. Yet preliminary calculations suggest the nucleus has retained much of its original composition, perhaps protected by an insulating layer of dust and organic compounds that accumulated during passage through dense molecular clouds. The comet's rotation period, measured at roughly 7 hours, speaks of angular momentum acquired through gravitational encounters during its galactic wandering. Unlike solar system comets, whose spins often reflect collisional histories within planetary formation regions, this visitor's rotation carries the signature of tidal forces exerted by massive stars and the differential gravitational effects of galactic structure. Each revolution reveals different facets of the nucleus to space, causing subtle variations in thermal absorption that will become critical when solar heating begins in earnest. Magnetic field measurements, obtained through radio astronomy techniques that detect plasma interactions in the solar wind, reveal that the visitor carries no intrinsic magnetism. This absence suggests formation in regions where magnetic fields played minimal roles in planetary accretion, perhaps in the outer regions of stellar systems where gas giant planets had swept away magnetically active debris, or in interstellar environments where the galactic magnetic field was too weak to influence small body formation. The lack of magnetic signature will later prove crucial in understanding how solar wind particles interact with the comet's developing coma. Spectroscopic analysis of reflected sunlight, though challenging at such great distances, begins to reveal surface composition details that distinguish the visitor from solar system natives. The absorption features indicate a surface enriched in organic compounds, not the complex carbon chemistry of terrestrial life, but simpler molecules like methanol, formaldehyde, and hydrogen cyanide that form readily in the cold, radiation-rich environment of interstellar space. These compounds, frozen solid at current temperatures, will provide the first visible signs of activity when solar heating begins to sublime them directly from solid to gas phase. The gravitational dynamics of the approach reveal subtle complexities that challenge conventional orbital mechanics. As the visitor enters the outer solar system's gravitational influence, perturbations from the giant planets Jupiter, Saturn, Uranus, and Neptune begin to modify its trajectory in ways that depend sensitively on the object's mass and internal structure. These gravitational deflections act like a cosmic scale, allowing astronomers to estimate the nucleus density and distinguish between loosely bound rubble pile structures and more consolidated single-body objects. What strikes observers as remarkable is the visitor's apparent immunity to the tidal forces that fragment many solar system comets during close stellar approaches. Computer simulations suggest the nucleus possesses sufficient structural integrity to survive perihelion passage intact, despite experiencing temperature gradients and thermal stresses that would shatter more loosely consolidated objects. This resilience implies formation under conditions that favored compact accretion, perhaps in stellar formation regions where shock waves from nearby supernovae compressed and strengthened the original planetesimal population. The approach trajectory will carry the visitor through regions of space populated by solar system debris, dust particles shed by comets over millions of years, microscopic fragments of asteroids ground down by mutual collisions, and the tenuous plasma environment that extends the Sun's magnetic influence far beyond the orbit of Pluto. These encounters, though individually insignificant, begin to alter the visitor's pristine interstellar composition through processes that blur the distinction between native and foreign material in the outer solar system. Radio telescopes detect the first subtle changes in the solar wind's behavior as it encounters the visitor's tenuous magnetic environment. Though the comet itself carries no magnetic field, the gradual sublimation of charged particles from its surface creates a tiny perturbation in the stream of plasma flowing outward from the Sun. This interaction, measurable only through sensitive instruments, marks the beginning of the transformation from inert interstellar wanderer to active comet, a process that will accelerate dramatically as the approach continues toward the inner solar system. Temperature monitoring reveals the first measurable warming of the nucleus surface, a rise from 10 Kelvin to perhaps 12 Kelvin. Insufficient to trigger visible activity, but significant enough to begin altering the crystalline structure of surface ices. Water ice, harder than granite at these temperatures, begins the subtle molecular rearrangements that precede sublimation. Carbon dioxide ice, even more volatile than water, shows the earliest signs of structural change as absorbed solar energy begins to overcome the intermolecular forces holding the solid structure together. The visitor continues its patient fall toward the Sun, carrying within its frozen heart the chemical memory of stellar nurseries whose light has never illuminated Earth's skies. Approaching a rendezvous that will briefly transform this ancient wanderer into one of the most closely studied objects in the solar system, the first whisper of transformation begins at distances where Earth appears as nothing more than a pale blue suggestion, lost in the Sun's overwhelming glare. Solar photons, streaming outward at the speed of light, penetrate the uppermost layers of the visitor's nucleus with energy sufficient to break the molecular bonds that have held water ice in crystalline suspension for millions of years. The process starts slowly, almost imperceptibly, individual molecules gaining enough thermal energy to escape the solid matrix and drift away into the vacuum of space. At 15 astronomical units from the Sun, roughly the distance of Uranus, the comet's surface temperature rises to 30 Kelvin, still brutally cold by terrestrial standards, yet warm enough to trigger the sublimation of the most volatile compounds embedded in the nucleus. Carbon monoxide ice, with its weaker intermolecular bonds, responds first to this gentle heating. Molecules that have remained motionless since the visitor's formation begin to vibrate with increasing amplitude, eventually breaking free from their crystalline prison to form the first tenuous wisps of what will become the comet's atmosphere. This earliest outgassing creates no visible spectacle. The escaping molecules are far too sparse to scatter appreciable sunlight, and their velocities too low to form the dramatic jets and fountains that characterize active comets. Instead, they drift away from the nucleus at speeds measured in meters per second, following ballistic trajectories that carry them slowly outward from the comet's minuscule gravitational field. The process resembles a planetary exhale so gentle that only the most sensitive instruments can detect the molecular signature of sublimation beginning in the depths of interstellar ice. Spectroscopic measurements reveal the isotopic fingerprints of this escaping gas, providing the first direct analysis of material formed in stellar regions beyond our solar system's influence. The deuterium-to-hydrogen ratio in the sublimating water vapor differs subtly but measurably from values typical of solar system comets, reflecting nucleosynthetic processes that occurred under different stellar conditions. Heavy water molecules, with their extra neutron, tell stories of stellar formation regions where temperature and density conditions favor different chemical pathways than those that operated in our Sun's protoplanetary disk. The carbon monoxide escaping from deeper layers carries an even more exotic signature: isotopic ratios of carbon-12 to carbon-13 that point to formation in the vicinity of massive stars whose nuclear furnaces operated at higher temperatures and pressures than our Sun ever achieved. These stellar giants, burning hydrogen and helium at prodigious rates, enrich their surrounding medium with fusion products in proportions that became locked into the ices now sublimating in our solar system's outer reaches. Each molecule of carbon monoxide serves as a fossil messenger, carrying news of stellar processes that occurred light years away and epochs ago. What puzzles atmospheric dynamicists is the apparent randomness of the early outgassing patterns. Unlike solar system comets, which often develop preferential sublimation from regions of the nucleus that receive maximum solar heating, the visitor shows activity emerging from multiple locations with no obvious relationship to solar illumination angles. This behavior suggests a composition more heterogeneous than typical solar system objects, with volatile-rich pockets distributed throughout the nucleus rather than concentrated in specific layers or regions. The implication is formation through a different accretionary process, perhaps gradual accumulation in a stellar formation region where multiple episodes of volatile deposition created a complex internal structure. Thermal modeling reveals that heat penetration into the nucleus proceeds more slowly than expected for objects of similar size within our solar system. The visitor's surface appears to possess unusually low thermal conductivity, possibly due to the presence of organic compounds that formed during its interstellar journey. These materials, created through radiation processing of simpler molecules over millions of years, act as an insulating layer that delays the warming of interior ices and creates temperature gradients unlike those found in native solar system comets. The developing coma, the tenuous atmosphere of gas and dust surrounding the nucleus, begins to interact with the solar wind in ways that reveal the visitor's alien origins. Plasma physicists detect unusual magnetic field configurations as charged particles from the Sun encounter the escaping cometary material. The interaction patterns differ from those observed around solar system comets, suggesting different compositions or different molecular dissociation processes in the coma. These subtle variations provide clues about the magnetic environment present when the visitor originally formed, possibly indicating birth in regions where stellar magnetic fields were weaker or oriented differently than in our solar neighborhood. Radio astronomy observations detect the first emission lines characteristic of excited water vapor and carbon monoxide in the expanding coma. The relative intensities of these spectral features encode information about the excitation conditions present as molecules transition from solid ice to gaseous form. The energy levels populated in these molecules reflect not only the current solar heating, but also the crystalline structure from which they sublimated, essentially providing a molecular memory of formation conditions preserved across interstellar distances and cosmic timescales. Dust particles, microscopic fragments of rocky material embedded in the sublimating ice, begin their own slow escape from the nucleus surface. These grains, typically smaller than bacteria and composed primarily of silicate minerals and organic compounds, carry the accumulated chemical signature of stellar formation processes that operated under different conditions than those in our solar system. Their mineral compositions, once analyzed through infrared spectroscopy, will reveal details about stellar winds, supernova shock waves, and the gradual chemical evolution of the interstellar medium in regions far from our Sun's influence. The visitor's rotation becomes increasingly evident as thermal emissions from different facets of the nucleus create a subtle but measurable light curve. The 7-hour rotation period, combined with the asymmetric heating pattern created by solar illumination, generates periodic variations in outgassing that serve as a natural clock marking the comet's spin. This rotational signature will prove crucial for understanding the nucleus shape and internal structure as activity levels increase during the approach to perihelion. Ground-based telescopes begin to detect the first optical evidence of cometary activity as scattered sunlight from dust particles in the developing coma creates a faint nebulosity around the nucleus. This initial appearance marks the visitor's transformation from invisible wanderer to detectable comet, though the brightness remains so low that only the most sensitive astronomical instruments can distinguish it from the stellar background. The light scattered by these particles carries polarization signatures that reveal details about grain size distributions and compositions, providing indirect measurements of the conditions present when the original planetesimals formed in distant stellar systems. What remains mysterious is the apparent correlation between outgassing activity and the visitor's magnetic environment as measured by spacecraft in the outer solar system. Subtle variations in activity levels seem to correspond with changes in the interplanetary magnetic field, the extension of the Sun's magnetic influence that pervades the space between planets. This correlation suggests that charged particle interactions play a more significant role in triggering sublimation than previously understood, possibly through electrical heating effects that supplement direct solar warming of the nucleus surface. The escaping gas and dust begin to feel the subtle pressure of solar radiation and the solar wind, forces that will eventually sculpt the characteristic tail structures associated with active comets. For now, these pressures remain too weak to create visible tail formation, but sensitive measurements detect the first signs of preferential acceleration of smaller particles away from the Sun. This process, known as radiation pressure, depends on particle size and composition in ways that will eventually sort the cometary debris according to physical properties, creating distinct tail components with different optical characteristics. As the visitor continues its approach through the outer solar system, each passing day brings slightly more intense solar heating and correspondingly increased sublimation activity. The ancient ice that has preserved interstellar conditions for millions of years begins its irreversible transformation to gas and dust, releasing molecular fossils into our solar system's environment and providing unprecedented opportunities to study material formed under stellar conditions vastly different from those that created our planetary neighborhood. Beyond the orbit of Neptune, where sunlight arrives with less than 1,000th the intensity it carries at Earth's distance, the visitor enters the gravitational realm that has shaped our solar system's architecture for 4.5 billion years. Here, in the scattered disk where Pluto traces its eccentric path and countless smaller objects follow orbits disturbed by ancient planetary migrations, the comet encounters the first substantial gravitational influences it has felt since leaving its stellar birthplace. The Sun's gravity well deepens perceptibly with each passing day, accelerating the visitor toward velocities that will eventually exceed 40 kilometers per second at perihelion. The nucleus continues to warm under the patient influence of distant solar radiation. Surface temperatures rise to 50 Kelvin, still cold enough to freeze nitrogen solid, yet sufficient to trigger more vigorous sublimation of carbon dioxide ice embedded in the visitor's outer layers. This secondary volatile, more responsive to heating than water ice but less volatile than carbon monoxide, begins to escape in quantities measurable by infrared spectrometers sensitive to its characteristic absorption wavelengths. The escaping carbon dioxide carries with it microscopic dust particles, creating the first visible signs of dust emission that will eventually develop into the comet's distinctive tail structures. Spectroscopic analysis of the sublimating gases reveals compositional details that distinguish the visitor from any object previously studied in our solar system. The ratio of carbon monoxide to water vapor exceeds values observed in native comets by factors of 10 or more, suggesting formation in environments where carbon chemistry proceeded along different pathways than those that operated in our Sun's protoplanetary disk. This carbon enhancement points to birth regions enriched by stellar winds from massive stars, objects whose nuclear furnaces operated at temperatures high enough to forge carbon atoms in abundance before dispersing them through supernova explosions. The developing coma begins to exhibit structure as differential heating of the nucleus surface creates preferential sublimation from regions facing the Sun. High-resolution imaging reveals subtle asymmetries in the gas and dust distribution, with material escaping more vigorously from areas where solar illumination encounters fresh ice exposure created by the visitor's rotation. These jets, invisible to the naked eye but detectable through long-exposure photography, follow trajectories determined by the nucleus's rotation and the balance between solar radiation pressure and the comet's weak gravitational field. Thermal modeling suggests that heat conduction into the nucleus interior proceeds through a complex medium of ice, dust, and organic compounds mixed in proportions unlike those found in solar system objects. The visitor's internal structure appears to consist of distinct layers or pockets of different compositions, possibly reflecting multiple episodes of accretion during its formation. This heterogeneous architecture creates thermal gradients that delay and complicate the sublimation process, leading to outgassing patterns that defy simple models based on solar system comet behavior. What intrigues planetary scientists is the apparent absence of water ice sublimation despite temperatures that should trigger significant outgassing from this most abundant volatile component. Ground-based spectroscopy detects strong carbon monoxide and carbon dioxide emission lines, but finds water vapor signals weaker than predicted for a typical comet at this solar distance. This behavior suggests either an unusual surface composition, heavily depleted in water ice, or a protective layer that inhibits water sublimation while allowing more volatile compounds to escape more readily. The visitor's dust production rate, estimated through analysis of scattered sunlight in the growing coma, reveals grain-size distributions that differ markedly from those observed in solar system comets. The particles appear to be systematically smaller, with peak abundances at sizes measured in tens of nanometers rather than the micrometers typical of native objects. These tiny grains, smaller than the wavelength of visible light, scatter sunlight with efficiency curves that create distinctive optical signatures detectable through multi-wavelength photometry. Their small size suggests formation through different aggregation processes, possibly gradual accretion in low-density environments rather than the collisional grinding that shapes dust in typical planetary formation regions. Radio telescopes detect the first hydroxyl radical emissions as water molecules in the coma dissociate under the influence of solar ultraviolet radiation. These OH radicals, created when solar photons break apart water molecules that have sublimated from the nucleus ice, emit characteristic radio wavelengths that serve as remote sensors for water production rates. The hydroxyl emission patterns reveal water vapor production levels significantly lower than expected for a comet of the visitor's estimated size, confirming the spectroscopic observations of anomalously low water content in the developing coma. Magnetic field measurements obtained through spacecraft instrumentation in the outer solar system detect subtle perturbations in the interplanetary magnetic environment as the solar wind encounters the visitor's expanding coma. These interactions, though weak compared to those observed around active solar system comets, provide insights into the electrical conductivity and plasma physics of material sublimating from interstellar ice. The magnetic signature suggests that the escaping gas carries charge distributions different from typical cometary plasma, possibly reflecting different molecular ionization potentials in the visitor's exotic composition. The comet's approach trajectory carries it through regions of space where the solar wind density and velocity undergo seasonal variations linked to solar activity cycles. These changes in the interplanetary medium create corresponding variations in the pressure forces acting on the escaping gas and dust, modulating the development of the coma in ways that encode information about both solar physics and cometary composition. Plasma physicists use these natural experiments to probe the interaction between stellar winds and interstellar material under controlled conditions impossible to replicate in terrestrial laboratories. Photometric observations reveal that the visitor's brightness increases more slowly than expected based on models derived from solar system comet behavior. The relationship between solar distance and activity level, normally described by power laws that reflect the temperature dependence of ice sublimation, shows systematic deviations that suggest different thermal properties or compositional variations in the nucleus interior. These anomalies provide clues about formation processes that operated under physical conditions unlike those present in our solar system's early history. Ground-based observatories begin coordinated monitoring campaigns as the visitor's brightness increases sufficiently for detailed spectroscopic analysis. Each telescope contributes different wavelength coverage and sensitivity, building a comprehensive picture of the comet's composition and activity patterns. Infrared observations reveal the thermal emission signatures of warm dust grains, while ultraviolet measurements probe the electronic transitions of excited molecules in the coma. Visible light spectroscopy detects the emission lines of neutral atoms and simple molecules, providing direct measurements of elemental abundances in material formed around other stars. The nucleus rotation becomes clearly evident as periodic variations in brightness and spectroscopic line intensities trace the 7-hour spin period with increasing precision. Different facets of the nucleus exhibit varying degrees of sublimation activity, creating a complex light curve that encodes information about surface composition variations and internal structure. The rotational signature serves as a natural probe of the nucleus shape and mass distribution, revealing an object that likely experienced collisional evolution during its interstellar journey through encounters with other wandering debris. As the visitor continues its approach toward the inner solar system, the subtle signs of activity detected in the outer reaches herald the dramatic transformation that awaits when solar heating intensifies beyond the critical thresholds that govern ice sublimation rates. The ancient material preserved in its nucleus, carrying chemical signatures from stellar formation regions light-years distant, prepares to reveal secrets about galactic evolution and planetary formation processes that operated under conditions vastly different from those that shaped our Earth and neighboring worlds. Jupiter's gravitational influence reaches across the solar system like an invisible web, bending space-time in patterns that have sculpted planetary orbits for billions of years. As the visitor approaches the orbit of the solar system's largest planet, still over 5 astronomical units away, the gas giant's immense mass begins to exert subtle perturbations on the comet's hyperbolic trajectory. These gravitational effects, though tiny compared to the Sun's overwhelming pull, demonstrate the complex orbital mechanics that govern the motion of small bodies throughout our stellar neighborhood. The visitor's path curves slightly as it feels Jupiter's tidal influence, not the dramatic close encounter that might scatter a comet into interstellar space or capture it into a bound solar orbit, but a gentle deflection that slightly alters the timing and geometry of its approach to perihelion. Computer simulations reveal that without Jupiter's presence, the comet would arrive at its closest solar approach several hours earlier and along a trajectory shifted by thousands of kilometers. These seemingly minor adjustments will prove crucial in determining which ground-based telescopes achieve optimal viewing geometry during the visitor's brief period of maximum brightness. The gravitational deflection serves as a cosmic scale, allowing astronomers to estimate the visitor's mass through precise measurements of its orbital perturbations. The degree of trajectory modification depends directly on the comet's mass-to-area ratio, providing indirect constraints on its internal density and structural properties. These calculations suggest a nucleus density intermediate between loose rubble pile structures typical of some solar system comets and the more consolidated objects that form through accretional heating. The implied density points to formation processes that achieved moderate compaction without complete thermal processing. At 8 astronomical units from the Sun, roughly the distance of Jupiter's orbit, solar heating raises the visitor's surface temperature to nearly 100 Kelvin, cold enough to solidify carbon dioxide on Earth, but warm enough to trigger vigorous sublimation from the nucleus surface. Water ice begins to sublime at measurable rates for the first time, joining the carbon monoxide and carbon dioxide that have been escaping since the comet entered the outer solar system. This triple volatile combination creates a chemically complex coma unlike anything observed around solar system objects. Spectroscopic observations reveal the distinctive fingerprint of water vapor in the comet's expanding atmosphere through the characteristic emission lines of excited hydroxyl radicals created when solar ultraviolet radiation dissociates sublimating water molecules. The intensity of these OH emissions indicates water production rates significantly lower than expected for a comet at this solar distance, confirming earlier suspicions about the visitor's unusual composition. The water-to-carbon monoxide ratio differs from solar system values by factors of 50 or more, suggesting formation in stellar environments where oxygen chemistry followed drastically different pathways. The expanding coma begins to exhibit the first signs of structure as solar radiation pressure and the solar wind start to influence the motion of escaping gas and dust particles, smaller dust grains. Those with sizes comparable to the wavelength of visible light feel stronger acceleration from solar photons and begin to separate from the larger particles that respond primarily to gravitational forces. This size sorting process, operating according to principles of celestial mechanics that govern comet tail formation throughout the solar system, creates subtle brightness variations in different wavelength bands that encode information about particle size distributions and compositions. High-resolution imaging reveals jets of material escaping from discrete locations on the nucleus surface, creating patterns that trace the comet's 7-hour rotation period with remarkable precision. These jets, oriented along directions determined by the balance between local gravitational forces and gas pressure gradients, carry dust particles away from the nucleus at velocities of several meters per second. The jet morphology provides clues about the nucleus shape and internal structure, suggesting an elongated object with regions of varying volatile content distributed across its surface. Radio interferometry detects the first clear signals of molecular line emission from the coma as gas densities reach thresholds sufficient for collisional excitation of rotational transitions. Water vapor, carbon monoxide, and methanol molecules emit characteristic radio frequencies that serve as remote probes of temperature, density, and composition in different regions of the expanding gas cloud. The relative line intensities reveal excitation conditions that differ from those observed in solar system comets, possibly reflecting different molecular formation processes in the visitor's interstellar birth environment. Infrared observations reveal thermal emission from warm dust grains suspended in the coma, providing direct measurements of particle temperatures and size distributions. The dust temperature lags behind the gas temperature by amounts that depend on particle thermal properties and heat capacity, parameters that encode information about grain compositions and internal structures. Silicate grains, composed primarily of olivine and pyroxene minerals, show thermal signatures consistent with formation in stellar winds from evolved stars, while carbonaceous particles exhibit properties suggesting radiation processing during the visitor's interstellar journey. The visitor's magnetic environment begins to exhibit the characteristic signatures of an active comet as charged particles in the coma interact with the interplanetary magnetic field. Magnetometer measurements from spacecraft in the outer solar system detect bow shock formations and magnetic field draping patterns that indicate the development of a substantial plasma environment around the nucleus. These magnetic interactions provide insights into the electrical conductivity of cometary material and the ionization processes that occur when interstellar matter encounters stellar radiation. Plasma physicists observe unusual ion velocity distributions in the visitor's magnetosphere that suggest different molecular dissociation and ionization pathways than those operating around solar system comets. The exotic composition, particularly the enhanced carbon monoxide abundance, creates plasma chemistry dominated by CO+ ions rather than the water-derived H2O+ and OH+ species typical of native objects. These compositional differences produce distinct optical emissions in the comet's ion tail that serve as fingerprints of its interstellar origins. Ground-based observatories detect the first clear evidence of gas production variations correlated with the nucleus rotation as different surface regions with varying volatile content rotate into and out of direct solar illumination. The amplitude of these rotational modulations, combined with the known 7-hour period, provides constraints on the nucleus shape and the degree of compositional heterogeneity across its surface. The data suggest an object with distinct hemispheres or regions of different composition, possibly reflecting formation through the merger of smaller objects with different thermal histories. Jupiter's gravitational influence extends beyond simple trajectory modification to affect the tidal stresses experienced by the nucleus during its passage through the outer solar system. Though these tidal forces remain far too weak to fragment a consolidated object, they may trigger subtle changes in outgassing patterns by opening or closing fractures in the nucleus interior. Seismic waves generated by tidal flexing could redistribute volatile-rich material or create new pathways for gas escape, contributing to the complex activity patterns observed as the visitor continues its approach toward the inner solar system. The comet's dust production increases dramatically as surface temperatures rise above critical sublimation thresholds for embedded particle release. Microscopic grains, lifted from the nucleus surface by escaping gases, begin their complex journey through the inner solar system under the competing influences of solar gravity, radiation pressure, and electromagnetic forces. These particles, ranging in size from nanometers to micrometers, carry within their mineral structures the accumulated chemical history of stellar formation processes that operated in regions of the galaxy never directly observable through traditional astronomical techniques. As the visitor continues its gravitational dance with Jupiter while falling deeper into the Sun's influence, the interplay between planetary perturbations and increasing solar heating sets the stage for the more dramatic transformations that await in the inner solar system. The ancient ice and dust that have preserved interstellar conditions for millions of years prepare for their final release, carrying messages from distant stellar nurseries toward a brief but spectacular encounter with our star's intense radiation environment. The coma awakens like a planetary dawn spreading across the darkness of space. What began as invisible molecular escape from the visitor's frozen surface transforms into a tenuous atmosphere extending thousands of kilometers from the nucleus, creating the characteristic fuzzy appearance that distinguishes active comets from the sharp, stellar points of more distant objects. This atmospheric envelope, composed primarily of water vapor, carbon dioxide, and the exotic abundance of carbon monoxide that marks the visitor's interstellar origins, begins to scatter sunlight with sufficient intensity for ground-based telescopes to resolve its structure and composition. At 6 astronomical units from the Sun, solar heating drives surface temperatures toward 150 Kelvin, still cold enough to freeze Mercury solid, yet warm enough to trigger vigorous sublimation from multiple volatile species embedded throughout the nucleus. The sublimation process operates through mechanisms that bypass the liquid phase entirely, transforming solid ice directly into gaseous form through the addition of thermal energy. This solid-to-gas transition, fundamental to cometry physics throughout the solar system, proceeds at rates determined by the vapor pressures of different molecular species and the efficiency of heat conduction through the nucleus interior. Water ice sublimation accelerates exponentially as temperatures rise above critical thresholds that have remained constant since the formation of the solar system. The visitor produces water vapor at rates approaching several tons per second, quantities that seem enormous by terrestrial standards, but represent merely the gentle exhale of an object whose total mass exceeds 10 billion tons. Each water molecule that escapes carries approximately 50,000 times more energy than was required to lift it from the nucleus surface. Energy provided by solar photons that have traveled 93 million miles to trigger this ancient transformation. The expanding gas cloud creates pressure gradients that accelerate dust particles away from the nucleus surface at velocities determined by the balance between gas drag forces and gravitational attraction. Microscopic grains, composed of silicate minerals and organic compounds that formed in stellar environments vastly different from our solar system, begin their journey through interplanetary space carrying chemical signatures of galactic evolution. These particles, ranging in size from nanometers to micrometers, follow trajectories governed by the same celestial mechanics that shape planetary motion throughout the universe. Spectroscopic analysis reveals the distinctive emission lines of excited molecules as they absorb and re-emit solar ultraviolet radiation in the low-density environment of the coma. Water molecules dissociate under photolysis to create hydroxyl radicals and hydrogen atoms, each following different velocity distributions that spread the spectral lines into Doppler-broadened profiles. These line shapes encode information about gas temperatures, expansion velocities, and the three-dimensional structure of the coma that cannot be obtained through any other observational technique. The visitor's exotic composition manifests most clearly in the unprecedented abundance of carbon monoxide emission lines that dominate the radio spectrum at frequencies corresponding to molecular rotational transitions. Ground-based radio telescopes detect CO emission intensities 50 times stronger than observed in typical solar system comets, confirming the visitor's formation in stellar environments where carbon chemistry proceeded along pathways unknown in our solar neighborhood. The carbon monoxide molecules, preserved in crystalline ice for millions of years, now escape into space carrying isotopic signatures of nuclear fusion processes that occurred in the cores of massive stars. Infrared observations reveal thermal emission from dust particles suspended throughout the coma, providing direct measurements of grain temperatures and size distributions that reflect both current solar heating and the thermal properties acquired during the visitor's interstellar journey. The dust temperature distribution shows systematic variations with distance from the nucleus that indicate ongoing sublimation processes, releasing fresh particles from the surface. Larger grains retain heat longer and exhibit thermal inertia effects that delay their temperature response to changing solar illumination, creating a complex thermal environment within the expanding dust cloud. High-resolution imaging begins to resolve the internal structure of the coma as differential gas production from various regions of the nucleus creates jets and streams of enhanced brightness. These features, visible through their enhanced dust content rather than direct gas emission, trace spiral patterns in the coma that reflect the nucleus rotation combined with the radial expansion of sublimated material. The jet morphology provides constraints on the nucleus shape and surface composition variations, revealing an object with distinct regions of enhanced volatile content separated by areas of lower activity. The developing coma begins to interact more significantly with the solar wind as gas densities reach levels sufficient to deflect the stream of charged particles flowing outward from the Sun. Magnetometer measurements detect the formation of a bow shock upstream from the comet, where the solar wind encounters resistance from the expanding gas cloud. This interaction creates a complex magnetospheric environment that channels plasma flow around the coma and begins the processes that will eventually form the visitor's distinctive ion tail. Plasma physics observations reveal unusual ion compositions in the visitor's magnetosphere that reflect the exotic molecular species sublimating from the nucleus, carbon monoxide ions. Rare in solar system comet plasmas, but abundant around the visitor, create distinct optical emission lines in the blue and ultraviolet wavelength ranges that serve as unmistakable signatures of interstellar origin. These ions, accelerated by electromagnetic forces in the comet's plasma environment, will eventually form the straight, blue-tinted ion tail characteristic of active comets throughout the solar system. The coma's optical properties begin to exhibit the characteristic wavelength dependence of Rayleigh scattering as dust particle sizes become comparable to the wavelengths of visible light. This scattering process, identical to the atmospheric physics that creates Earth's blue skies, gives the inner coma regions a subtle blue tint that distinguishes them from the more neutral colors of the outer dust cloud. Polarization measurements reveal systematic variations in the degree of linear polarization that encode information about particle shapes, sizes, and compositions not accessible through other observational techniques. Ground-based observatories detect periodic variations in coma brightness and spectroscopic line intensities that trace the nucleus rotation with increasing precision as activity levels rise. The 7-hour rotation period creates systematic modulations in gas and dust production as different surface regions rotate into and out of direct solar illumination. These rotational light curves provide insights into the degree of surface heterogeneity and the three-dimensional distribution of volatile-rich regions across the nucleus surface. The visitor's dust production begins to exhibit the first signs of tail formation as radiation pressure from sunlight starts to overcome the gravitational attraction of the nucleus for smaller particles. Grains, with sizes less than a few micrometers, feel stronger acceleration from absorbed and scattered solar photons, causing them to lag behind the nucleus in its orbital motion and creating the curved dust tail structure that will become increasingly prominent as the comet approaches perihelion. This tail formation process, operating according to principles of celestial mechanics that govern similar phenomena throughout the galaxy, transforms the visitor from a localized source of activity into an extended structure stretching millions of kilometers across space. The coma's chemical composition continues to evolve as solar heating penetrates deeper into the nucleus interior, accessing volatile-rich layers that have remained frozen since the visitor's formation. Each temperature increase unlocks new molecular species for sublimation, creating a complex chemical evolution that mirrors the thermal history of solar system formation but operates on material that originated under entirely different stellar conditions. As the visitor continues its approach toward the inner solar system, this awakening atmosphere prepares for the more dramatic transformations that await under the intense radiation environment near our star. Mars orbits the Sun in the transitional realm between the cold outer planets and the warm inner worlds, marking a boundary where solar radiation intensifies sufficiently to drive dramatic changes in cometary behavior. As the visitor crosses this invisible threshold at approximately 1.5 astronomical units from our star, surface temperatures rise beyond 200 Kelvin for the first time since its formation in distant stellar nurseries. This thermal milestone triggers cascading sublimation processes that transform the visitor from a moderately active comet into an object producing gas and dust at rates visible to the naked eye from Earth's surface. The nucleus surface, warmed by solar radiation, now carrying 10 times the intensity present at Jupiter's orbit, begins to exhibit complex thermal patterns that reflect both the visitor's rotation and the heterogeneous distribution of volatile materials across its surface. Infrared thermal mapping reveals temperature variations of 50 Kelvin or more between sun-facing and shadowed regions, creating thermal gradients steep enough to generate significant internal stresses within the nucleus structure. These temperature differences drive sublimation at varying rates across the surface, with some regions producing vigorous jets of gas and dust, while others remain relatively inactive despite receiving similar solar heating. Water-ice sublimation accelerates to production rates exceeding 10 tons per second as the visitor's distance from the Sun decreases below 2 astronomical units. This water vapor, derived from ice that condensed around dust grains in stellar formation regions light years from our solar system, now expands into space at velocities approaching 1 kilometer per second. The escaping water molecules carry kinetic energies sufficient to lift dust particles with diameters up to several millimeters away from the nucleus surface, creating a steady stream of debris that feeds the visitor's growing dust coma and tail structures. The exotic carbon monoxide content that distinguishes the visitor from all previously studied comets reaches production levels that create visible spectroscopic signatures detectable through modest ground-based telescopes. CO emission lines in the infrared spectrum now rival the intensity of water vapor transitions, despite carbon monoxide's much lower abundance in typical solar system objects. This enhanced CO production reflects formation conditions in stellar environments where carbon chemistry proceeded through pathways enriched by massive star nucleosynthesis, processes that operated at temperatures and pressures never achieved in our Sun's more modest nuclear furnace. Dust grain analysis through multi-wavelength photometry reveals particle compositions that bear the mineralogical signatures of stellar wind processing and interstellar radiation exposure accumulated over millions of years of galactic wandering. Silicate particles exhibit crystalline structures that formed at temperatures exceeding 1000 Kelvin, suggesting origins in the atmospheres of evolved stars where stellar winds carried newly formed minerals into interstellar space. These refractory grains, embedded in water ice during the visitor's accretion, now escape into our solar system, carrying direct samples of stellar nucleosynthesis from regions of the galaxy never accessible to Earth-based observations. The visitor's coma expands to dimensions approaching 100,000 kilometers in diameter, roughly 3/4 the distance between Earth and Moon, as gas production rates increase exponentially with decreasing solar distance. This tenuous atmosphere, with densities millions of times lower than Earth's air at sea level, nonetheless contains sufficient material to scatter sunlight and create the characteristic fuzzy appearance that transforms the visitor from a stellar point source into a clearly resolved cometary object visible through binoculars from Earth's surface. Plasma physics observations reveal the development of a substantial magnetospheric environment as the solar wind encounters increasing resistance from the expanding gas cloud surrounding the nucleus. The bow shock that forms upstream from the comet now extends several thousand kilometers, creating a complex three-dimensional structure that channels solar wind plasma around the coma and accelerates cometary ions to velocities approaching 100 kilometers per second. These accelerated ions, composed primarily of water group species and the unusual abundance of carbon monoxide ions, begin to form the straight ion tail that will become increasingly prominent as solar wind pressure intensifies closer to the Sun. High-resolution imaging resolves multiple jet structures emanating from discrete locations on the nucleus surface, creating a complex pattern of enhanced brightness regions that trace the comet's rotation with exquisite precision. The jets exhibit collimated structures extending thousands of kilometers from their source regions, maintaining coherence through gas dynamic processes that focus the expanding sublimation products into narrow beams. These collimated outflows carry dust particles along trajectories that depend sensitively on particle size and composition, creating sorting mechanisms that segregate different types of material according to their response to radiation pressure and electromagnetic forces. Ground-based spectroscopy detects the first clear signatures of minor molecular species that provide insights into the detailed chemical composition of interstellar ice, methanol, formaldehyde, and hydrogen cyanide, molecules that form readily in the radiation-rich environment of dense molecular clouds, begin to appear in the visitor's spectrum as surface temperatures rise sufficiently to sublime these less abundant but scientifically significant compounds. Each minor species carries information about the physical and chemical conditions present during the visitor's formation, providing glimpses into stellar formation processes that operated under conditions vastly different from those in our solar system. The dust tail begins to exhibit clear structure as radiation pressure sorts particles according to size and composition, creating streamers of material that trace the visitor's orbital motion through space. Smaller particles, those with sizes comparable to the wavelength of visible light, experience stronger acceleration from solar photons and separate from larger grains that respond primarily to gravitational forces. This size-dependent acceleration creates a curved tail structure that maps the visitor's orbital history and provides constraints on particle size distributions and compositions throughout the tail. Radio interferometry observations detect molecular line emission from increasingly exotic species as sublimation temperatures rise above thresholds required to release more refractory compounds from the nucleus interior: carbon dioxide, sulfur dioxide, and various organic molecules create characteristic emission signatures that serve as remote probes of the chemical inventory preserved in interstellar ice for millions of years. The relative abundances of these species reflect nucleosynthetic processes and stellar wind compositions that operated in the visitor's birth environment, providing direct measurements of stellar chemistry from regions of the galaxy beyond the reach of traditional astronomical observations. Thermal modeling reveals that heat conduction into the nucleus interior now reaches depths of several meters below the surface, accessing volatile-rich layers that have remained undisturbed since the visitor's formation. This thermal penetration creates complex sublimation patterns that depend on the three-dimensional distribution of different ice species throughout the nucleus structure. The resulting gas production exhibits temporal variations that encode information about internal stratification and the accretionary processes that assembled the visitor from smaller components in its stellar formation region. The visitor's activity level begins to approach the threshold values that will trigger the most dramatic phase of its transformation as it continues toward perihelion. Solar heating now drives sublimation processes at rates that substantially modify the nucleus surface on timescales measured in days rather than years, creating a dynamically evolving object whose properties change continuously under the influence of our star's intense radiation. The ancient material that has preserved interstellar conditions throughout its galactic journey now prepares for the climactic encounter that will briefly transform this wandering messenger into one of the most spectacular objects visible in Earth's sky. The mysterious deceleration appears first as tiny discrepancies in the visitor's predicted position against the stellar background, deviations measured in arcseconds that initially seem insignificant but grow more pronounced with each passing observation. Ground-based astrometry, the precise measurement of celestial positions that has guided navigation for centuries, detects systematic shifts in the comet's trajectory that cannot be explained by gravitational forces alone. The visitor moves more slowly than orbital mechanics predicts, as if some invisible force opposes its motion through space with a persistence that defies conventional understanding of solar system dynamics. At 1 astronomical unit from the Sun, the same distance that separates Earth from our star, the visitor experiences solar heating intense enough to drive water sublimation at rates exceeding 100 tons per second. Yet this massive gas production creates forces that act like microscopic rocket engines distributed across the nucleus surface, each jet of escaping vapor imparting momentum that slightly alters the comet's trajectory. The cumulative effect of millions of individual sublimation events creates what astronomers term the rocket effect, a non-gravitational acceleration that depends on the three-dimensional distribution of active regions across the nucleus surface. The physics underlying this phenomenon operates according to Newton's third law applied on a planetary scale. Every action produces an equal and opposite reaction. When water molecules escape from the sun-facing hemisphere of the nucleus, they carry momentum away from the comet, creating a tiny but measurable recoil that pushes the nucleus in the opposite direction. For most solar system comets, this rocket effect accelerates the object along its orbital path. But the visitor exhibits the opposite behavior, a systematic deceleration that suggests preferential outgassing from the trailing hemisphere as the nucleus rotates through its 7-hour spin cycle. High-precision radar observations from the Deep Space Network detect velocity changes measured in millimeters per second, tiny alterations that accumulate over days and weeks to produce positional shifts visible through optical telescopes. The magnitude of these non-gravitational forces depends sensitively on the visitor's mass, internal structure, and the asymmetry of gas production across its surface. Computer models suggest that even small variations in volatile distribution can generate rocket effects powerful enough to modify orbital trajectories by thousands of kilometers over the duration of a single apparition. The visitor's unusual composition, particularly its enhanced carbon monoxide content, creates sublimation patterns unlike those observed in any previous comet. Carbon monoxide sublimes at much lower temperatures than water ice, creating outgassing activity that persists on the night side of the nucleus where water ice remains frozen solid. This continuous CO emission from shadowed regions generates rocket forces with different directional components than the sun-facing water jets, creating a complex vector sum of accelerations that produces the observed deceleration rather than the acceleration typical of solar system objects. Thermal modeling reveals that the visitor's low thermal conductivity, possibly due to insulating layers of organic compounds accumulated during its interstellar journey, creates temperature lag effects that delay peak sublimation relative to maximum solar heating. This thermal inertia means that the most vigorous outgassing occurs not when surface regions face the sun directly, but hours later as conducted heat reaches subsurface ice deposits. The resulting phase lag between heating and gas production shifts the direction of rocket forces away from the purely radial pattern that would produce no net acceleration. Spectroscopic observations detect systematic variations in emission line intensities that correlate with the observed trajectory perturbations, providing direct evidence for the connection between gas production patterns and orbital dynamics. Water vapor emission reaches maximum intensity several hours after local noon on each facet of the rotating nucleus, while carbon monoxide emission shows less pronounced diurnal variations due to its ability to sublime from permanently shadowed regions. These compositional asymmetries create a complex pattern of forces that vary systematically with the nucleus rotation and orbital position. The magnitude of the observed deceleration, approximately 1 meter per second per day, seems minuscule by terrestrial standards, but represents enormous forces when integrated over the visitor's substantial mass. The total momentum change implied by these measurements equals the effect of a gentle breeze blowing continuously against an object the size of a mountain, demonstrating the cumulative power of processes that operate through the patient accumulation of countless microscopic events. This rocket effect will ultimately alter the visitor's trajectory by amounts sufficient to change its departure velocity from the solar system and modify its future galactic wandering path. Ground-based photometry reveals periodic brightness variations that trace the nucleus rotation while simultaneously encoding information about the three-dimensional distribution of active regions responsible for the non-gravitational forces. The amplitude and phase of these brightness oscillations provide constraints on surface composition, heterogeneity, and the geometric relationship between solar illumination and gas production sites. The data suggest a nucleus with distinct hemispheres or regional variations in volatile content that create preferential outgassing patterns as different areas rotate into and out of solar heating. Radio interferometry observations of molecular line emission detect Doppler shifts that trace the three-dimensional velocity structure of gas escaping from different regions of the nucleus surface. These velocity measurements provide direct evidence for asymmetric outgassing patterns that generate the observed rocket forces. Carbon monoxide emission shows systematic velocity offsets that indicate preferential escape from regions not directly facing the sun, while water vapor exhibits more conventional patterns of maximum emission from sun-facing areas during local daylight hours. The visitor's magnetospheric environment begins to exhibit signatures of the enhanced activity levels as increasing gas production creates denser plasma regions around the nucleus. Magnetic field measurements detect both shock structures that fluctuate in strength and position as gas production rates vary with the nucleus rotation and orbital position. These plasma interactions provide additional insights into the spatial distribution of outgassing sources and their relationship to the forces that perturb the comet's trajectory through space. Infrared thermal imaging resolves temperature patterns across the nucleus surface that reveal the thermal lag effects responsible for the delayed sublimation driving the rocket forces. Surface temperatures peak several hours after local solar noon, creating maximum gas production when the outgassing sites have rotated away from the subsolar point. This thermal behavior reflects the visitor's unusual thermal properties, possibly including low conductivity materials that insulate subsurface ice from rapid temperature changes and create the observed phase relationships between heating and sublimation. The systematic nature of the trajectory perturbations allows astronomers to predict future positions with unprecedented precision despite the non-gravitational forces acting on the nucleus. By incorporating models of asymmetric outgassing into orbital calculation codes, researchers achieve positional predictions accurate to within a few arcseconds over timescales of weeks to months. These refined ephemerides prove crucial for coordinating ground-based observations and optimizing telescope pointing during the visitor's brief period of maximum activity near Perihelion. Computer simulations reveal that the observed deceleration pattern places important constraints on the visitor's internal structure and formation history. The magnitude and direction of rocket forces depend sensitively on mass distribution within the nucleus, with consolidated objects producing different signatures than loose rubble pile structures. The data favor a moderately consolidated nucleus with heterogeneous composition, consistent with formation through gradual accretion in a stellar environment followed by partial thermal processing during the interstellar journey. As the visitor continues its approach toward perihelion, the rocket effect intensifies proportionally to gas production rates, creating increasingly large perturbations that accumulate to produce substantial changes in the departure trajectory from the solar system. These forces, invisible to casual observation but precisely measurable through modern astrometric techniques, demonstrate how microscopic physical processes can produce macroscopic consequences when operating continuously over astronomical timescales. The ancient wanderer that entered our solar system following one hyperbolic path will depart along a measurably different trajectory. Its future galactic journey altered by the subtle influence of our star's heating and the asymmetric response of interstellar ice to solar radiation. The escaping gases reveal their secrets through the language of light, each molecular species absorbing and emitting characteristic wavelengths that serve as fingerprints identifying their presence in the visitor's expanding coma. Ground-based spectrometers, sensitive instruments that spread starlight into component colors with precision measured in angstroms, detect absorption features that encode the detailed chemistry of material formed around other stars. Water vapor creates its distinctive signature through electronic transitions in the ultraviolet, while carbon monoxide molecules emit infrared photons at frequencies determined by their rotational energy levels and the temperature of the gas clouds surrounding the nucleus. The isotopic composition of sublimating water provides the most direct evidence of the visitor's interstellar origins through measurements of heavy water, molecules containing deuterium atoms instead of ordinary hydrogen. The ratio of deuterium to hydrogen in terrestrial water reflects nucleosynthetic processes that operated in our Sun's protoplanetary disk 4.5 billion years ago. But the visitor's water exhibits deuterium enrichment levels that point to formation in stellar environments where different nuclear fusion pathways created distinct isotopic signatures. Each heavy water molecule serves as a fossil record of stellar evolution processes that operated under physical conditions never achieved in our solar system. Carbon isotope ratios in the abundant carbon monoxide emission reveal even more exotic signatures of stellar nucleosynthesis from the visitor's birth region. The proportion of carbon 13 to carbon 12 in the escaping CO molecules differs significantly from solar system values, indicating formation in environments enriched by nuclear burning processes in massive stars. These stellar giants, with cores hot enough to fuse carbon atoms through the CNO cycle, dispersed fusion products with isotopic signatures that became incorporated into the interstellar medium from which the visitor eventually condensed. The carbon isotope data provides direct measurements of stellar evolution processes that occurred light years away and millions of years before our Sun formed. Oxygen isotope measurements, obtained through high-resolution spectroscopy of water vapor and carbon dioxide emission lines, reveal three isotope relationships that distinguish solar system from interstellar material with remarkable precision. The visitor's oxygen-16 to oxygen-18 ratio follows patterns characteristic of stellar winds from evolved stars rather than the mass-dependent fractionation processes that shaped oxygen isotopes in our Sun's protoplanetary disk. These measurements provide insights into stellar evolution phases that enrich the interstellar medium with oxygen isotopes in proportions reflecting nuclear burning processes fundamentally different from those operating in our star. Nitrogen isotope analysis through observations of hydrogen cyanide and ammonia emission lines reveals isotopic signatures that reflect the complex chemistry operating in dense molecular clouds where the visitor formed. The nitrogen-14 to nitrogen-15 ratio encodes information about ion molecule reaction networks that operated in the cold, radiation-rich environment of stellar formation regions. These chemical processes, involving ion exchange reactions between nitrogen-bearing molecules and cosmic ray particles, created isotopic fractionation patterns that became frozen into the visitor's ice matrix and now provide windows into the physical conditions present during its accretion. Rare gas measurements, though challenging to obtain due to their chemical inertness and low abundances, offer perhaps the most definitive proof of interstellar origin through isotopic compositions that cannot be modified by subsequent chemical processing. Argon isotope ratios in the visitor's coma, measured through ultraviolet spectroscopy of ionized gas in the expanding plasma environment, exhibit signatures of stellar nucleosynthesis from multiple stellar generations. The argon-36 to argon-38 ratio reflects neutron capture processes operating in the interiors of massive stars, while argon-40 abundances indicate contributions from potassium decay in stellar environments with different age and metallicity than our solar neighborhood. The sulfur isotope signature, revealed through sulfur dioxide emission lines detectable at radio wavelengths, provides constraints on the visitor's formation environment through isotopic ratios that reflect nuclear burning processes in stellar cores. Sulfur 32 to sulfur 34 ratios point to nucleosynthetic contributions from stars with masses exceeding 20 solar masses, objects that undergo core collapse supernovae and disperse their nuclear-burning products into the surrounding interstellar medium. The visitor's sulfur isotopes carry direct evidence of these violent stellar death events, preserving chemical signatures of supernova nucleosynthesis from regions of the galaxy where stellar evolution proceeded along pathways unknown in our Sun's more modest stellar neighborhood. Multi-element abundance patterns, obtained by comparing emission line intensities across the electromagnetic spectrum, reveal elemental ratios that distinguish the visitor from all previously analyzed solar system materials. The carbon-to-oxygen ratio exceeds solar system values by factors of 3, while nitrogen abundances relative to oxygen indicate formation in environments where stellar winds from massive stars contributed disproportionate amounts of CNO-processed material. These abundance patterns serve as chemical DNA that identifies the visitor's stellar parentage and provides insights into galactic chemical evolution processes operating in regions beyond our solar system's immediate neighborhood. Organic molecule detection through infrared spectroscopy reveals complex carbon chemistry that developed during the visitor's interstellar journey through radiation processing of simpler compounds. Methanol, formaldehyde, and more complex organic species exhibit abundance ratios that reflect chemical networks operating in the cold, high radiation environment of interstellar space. These molecules, formed through reactions between cosmic ray particles and simple ices over millions of years, provide direct samples of interstellar chemistry processes that cannot be replicated in terrestrial laboratories due to the extreme timescales and radiation environments required. The molecular complexity revealed through spectroscopic analysis suggests chemical processing pathways that operated continuously during the visitor's galactic wandering. Polycyclic aromatic hydrocarbons, detected through their characteristic infrared emission features, indicate exposure to stellar ultraviolet radiation fields with intensities and spectral distributions different from those in our solar neighborhood. These complex organic molecules, synthesized through photochemical reactions in the visitor's surface layers, carry information about the radiation environments encountered during its interstellar journey across multiple stellar formation regions. Volatile element depletion patterns, revealed through comparisons of observed abundances with theoretical models of interstellar ice composition, provide constraints on thermal processing that occurred during the visitor's formation or subsequent evolution. Elements with low condensation temperatures show systematic depletions relative to refractory species, indicating either formation in warmer stellar environments or thermal processing during close encounters with other stars during the galactic journey. These depletion patterns serve as thermometers recording maximum temperatures experienced by the visitor's constituent materials. High-resolution spectroscopy resolves velocity structures within individual emission lines that encode information about gas dynamics and temperature gradients in the expanding coma. Doppler line profiles reveal systematic velocity shifts that trace the three-dimensional expansion pattern of sublimated gases, while line width measurements provide gas temperature determinations independent of thermal modeling assumptions. These kinematic measurements reveal expansion patterns, unlike those observed in solar system comets, possibly reflecting different sublimation physics operating on interstellar ice compositions. The spectroscopic data accumulates into a comprehensive chemical inventory that reads like a textbook of stellar evolution and galactic chemical enrichment processes written in the language of atomic and molecular physics. Each emission line contributes another piece to a chemical puzzle that reveals the visitor's origins in stellar formation regions where nuclear fusion, stellar winds, and supernova explosions operated under conditions vastly different from those that shaped our solar system. The ancient ice, now sublimating in our sun's radiation, carries within its molecular structure the accumulated history of stellar generations that lived and died in regions of the galaxy whose light has never reached Earth's telescopes, providing unprecedented insights into cosmic chemical evolution processes operating on scales both spatial and temporal that dwarf human experience. At 3/4 of an astronomical unit from the Sun, where Mercury completes its swift orbital dance and solar radiation carries 4 times the intensity present at Earth's distance. The visitor encounters a phenomenon that defies conventional understanding of cometary behavior. Instead of the dramatic surge in activity that should accompany such intense solar heating, the comet's gas and dust production rates begin to plateau and then mysteriously decline. This unexpected pause in sublimation activity occurs precisely when theoretical models predict maximum outgassing, creating a puzzling contradiction that challenges fundamental assumptions about the physics of interstellar ice under stellar radiation. Surface temperatures now exceed 300 Kelvin across sun-facing regions of the nucleus, hot enough to sublime water ice at prodigious rates that should create visible jets and dramatically enhance the coma brightness. Yet ground-based observations detect activity levels that remain stubbornly constant or even decrease slightly as solar distance continues to diminish. The visitor behaves as if some protective mechanism shields its volatile inventory from the sun's increasingly intense radiation, creating thermal conditions that somehow resist the exponential relationship between temperature and sublimation rate that governs all previously studied comets. Infrared thermal mapping reveals the development of a dark, desiccated layer across much of the nucleus surface, a lag deposit composed of dust and organic compounds left behind as the more volatile ice components sublime away. This residual material, enriched in refractory particles and complex carbon compounds that accumulated during the visitor's interstellar journey, acts like thermal insulation that impedes heat conduction to subsurface ice reservoirs. The lag deposit creates a feedback mechanism where initial sublimation activity generates its own suppression by building up protective layers that isolate interior volatiles from further solar heating. The formation of this insulating mantle operates through processes that reflect the visitor's exotic composition and unusual thermal properties. Unlike solar system comets, whose surfaces typically consist of relatively clean water ice mixed with silicate dust, the visitor's nucleus contains substantial quantities of organic compounds synthesized during millions of years of cosmic ray exposure in interstellar space. These carbonaceous materials, with melting points well above water, ice sublimation temperatures, remain solid even under intense solar heating and accumulate to form surface layers that dramatically reduce thermal conductivity. Spectroscopic observations detect subtle changes in the relative abundances of different molecular species in the coma as the strange pause develops. Water vapor production decreases more rapidly than carbon monoxide emission, suggesting that the protective surface layer affects different volatile species to varying degrees. Carbon monoxide, with its lower sublimation temperature and smaller molecular size, continues to escape through micropores and fractures in the lag deposit that remain impermeable to larger water molecules. This selective permeability creates compositional fractionation effects that progressively alter the visitor's coma chemistry as the insulating layer thickens. High-resolution imaging reveals that the pause in activity affects different regions of the nucleus surface to varying degrees, creating a complex mosaic of active and inactive areas that changes systematically as the visitor rotates through its 7-hour spin cycle. Some surface regions maintain vigorous outgassing throughout the pause period, possibly due to recent exposure of fresh ice through fracturing or mass wasting processes that break through the protective lag deposit. These active areas appear as bright jets in the coma images, while surrounding regions show dramatically reduced dust production, despite receiving similar solar heating. The thermal physics underlying the pause phenomenon involves complex interactions between radiative heating, conductive heat transfer, and sublimation cooling that operate simultaneously across the nucleus surface. Solar energy absorbed by the dark surface layer raises temperatures well above water ice sublimation points. But the low thermal conductivity of organic-rich lag deposits prevents this heat from reaching subsurface ice reservoirs, where most of the visitor's volatile inventory remains stored. The result is surface layers that become hot enough to glow in thermal infrared wavelengths, while interior ice remains at temperatures insufficient to drive significant sublimation. Ground-based radar observations detect changes in the surface roughness and radar reflectivity that indicate ongoing modification of the nucleus surface properties during the pause period. The development of the protective lag deposit alters surface scattering characteristics in ways that encode information about layer thickness and composition. Radar echoes reveal surface features that suggest active erosion and mass-wasting processes operating even during the period of reduced volatile activity, indicating that solar heating continues to drive physical evolution of the nucleus structure through thermal expansion and contraction cycles. Plasma physics measurements reveal that the visitor's magnetospheric environment undergoes systematic changes during the strange pause as gas production rates plateau despite increasing solar wind pressure and magnetic field strength. The bow shock that forms upstream from the comet becomes smaller and less well-defined as the balance between gas production and solar wind momentum flux shifts towards solar wind dominance. These plasma environment changes affect the acceleration of cometary ions and the formation of the ion tail, creating observable signatures of the reduced activity levels that can be detected through ground-based spectroscopy. The dust tail morphology exhibits distinctive changes during the pause period as reduced gas production alters the velocity distribution of particles escaping from the nucleus surface. Larger dust grains, which depend on gas drag forces for initial acceleration away from the nucleus, show decreased escape velocities that modify the curvature and brightness distribution of the dust tail. Smaller particles, still lifted efficiently by the reduced gas flow, continue to populate the tail but create different optical depth profiles that change the tail's scattering properties and overall appearance. Computer modeling reveals that the pause phenomenon results from the interplay between multiple physical processes operating on different timescales and spatial scales throughout the nucleus structure. Surface heating occurs rapidly, within hours of solar illumination, while heat conduction to subsurface layers requires days or weeks depending on thermal diffusivity and layer thickness. Sublimation rates depend exponentially on temperature, creating strong feedback between thermal conditions and volatile loss rates that can produce bistable behavior where small changes in surface properties trigger large changes in activity levels. The chemical composition of escaping gases shows systematic evolution during the pause period as the protective lag deposit creates selective effects on different volatile species. More volatile compounds like carbon monoxide continue to escape at rates determined primarily by subsurface temperatures, while less volatile species like water vapor become increasingly dominated by sublimation from localized areas where lag deposit thickness remains minimal. This compositional evolution creates time-dependent spectroscopic signatures that provide remote sensing capabilities for monitoring subsurface thermal conditions and volatile inventory. Radio interferometry observations detect changes in molecular line ratios that reflect the evolving thermal conditions within the nucleus interior as heat conduction patterns adjust to the presence of the insulating surface layer. Temperature-sensitive line intensity ratios provide thermometric measurements that reveal the three-dimensional temperature distribution within the coma, and, by inference, the thermal conditions at different depths within the nucleus structure. These measurements suggest internal temperature gradients that become increasingly steep as the surface insulation develops during the pause period. The strange pause phenomenon demonstrates the complex interplay between composition, thermal physics, and evolutionary processes that can create behaviors in interstellar objects fundamentally different from those observed in solar system natives. The visitor's exotic chemistry, accumulated during millions of years of galactic wandering, produces thermal and physical responses to solar heating that operate according to different rules than those governing familiar cometary phenomena. This unexpected behavior provides insights into the diversity of physical processes that shape small bodies throughout the galaxy and highlights the importance of direct observations for understanding objects formed under conditions vastly different from those in our solar system. As the visitor continues its approach toward Perihelion, the strange pause creates uncertainty about the intensity of activity that will develop during closest solar approach. The protective mechanisms that currently suppress sublimation may prove temporary, with dramatic activity resumption possible if thermal penetration eventually overwhelms the insulating effects of the lag deposit, or the pause may persist through perihelion, creating a visitor that remains mysteriously quiescent despite experiencing the most intense heating of its solar system encounter. Perihelion arrives with the precision of celestial mechanics, 39 astronomical units from the Sun, closer than Mercury's orbit, where solar radiation carries 27 times the intensity present at Earth's distance and surface temperature stertions should exceed 500 Kelvin across sun-facing regions of the nucleus, yet the visitor's response to this intense heating remains curiously muted, defying theoretical predictions that call for explosive sublimation activity and brilliant coma development. Instead of the dramatic spectacle expected from such close solar approach, the comet maintains activity levels only marginally higher than those observed during its strange pause, creating a perihelion passage that puzzles observers worldwide. The nucleus surface, now receiving solar flux equivalent to half a kilowatt per square meter, develops extreme temperature gradients between illuminated and shadowed regions that create thermal stresses sufficient to fracture solid rock. Thermal expansion and contraction cycles, operating on the 7-hour timescale of the nucleus rotation, generate mechanical forces that should expose fresh ice through surface disruption and create new pathways for volatile escape. Yet high-resolution imaging reveals surface modifications that appear limited to subtle changes in brightness patterns and the gradual expansion of existing dust deposits rather than the dramatic restructuring expected under such intense thermal processing. The mysterious restraint in activity levels becomes more pronounced when compared to solar system comets at similar solar distances. Native objects typically exhibit gas production rates exceeding 1,000 tons per second at perihelion, creating spectacular visual displays visible to the naked eye from Earth. The visitor produces gas at rates barely 1/10 these values, despite possessing comparable nuclear dimensions and presumably similar volatile inventories. This suppressed activity suggests either fundamental differences in composition or the operation of physical processes that remain poorly understood even after decades of cometary research. Spectroscopic analysis reveals that the exotic carbon monoxide content continues to dominate the visitor's chemical signature even at perihelion, where water vapor emission from most comets overwhelms all other molecular species. The CO2-water ratio remains elevated by factors of 50 compared to solar system objects, indicating that the protective mechanisms suppressing water ice sublimation do not equally affect carbon monoxide escape. This selective suppression creates compositional signatures that become increasingly distinct from typical cometary spectra as solar heating intensifies, providing definitive proof of the visitor's interstellar origins through chemical behavior impossible to replicate in native solar system objects. Infrared. Thermal emission measurements detect surface temperatures that exceed predictions based on simple radiative equilibrium models, suggesting that absorbed solar energy accumulates in surface layers rather than driving efficient sublimation processes. The dark lag deposit that developed during the strange pause now covers much of the nucleus surface with insulating material that creates temperature profiles fundamentally different from those in typical comets. Heat conduction through this organic-rich layer proceeds slowly enough that surface temperatures can rise well above sublimation thresholds for subsurface ice, while interior volatiles remain thermally isolated from the intense solar heating. The plasma environment surrounding the visitor exhibits characteristics that reflect both the reduced gas production and the enhanced solar wind pressure present at perihelion distance. Magnetometer measurements detect bow shock structures that remain surprisingly weak despite the comet's proximity to the Sun, indicating that escaping gas densities never reach levels sufficient to create substantial solar wind deflection. The ion tail, fed primarily by carbon monoxide ions rather than the water group species typical of solar system comets, maintains its distinctive blue coloration but exhibits brightness levels that plateau rather than increase exponentially as expected for objects at perihelion distance. Ground-based photometry reveals brightness variations that trace the nucleus rotation with amplitude modulations that encode information about surface heterogeneity and the three-dimensional distribution of active regions. The 7-hour rotation period creates systematic brightness oscillations that reach maximum amplitude during perihelion passage, suggesting that solar heating enhances contrast between regions of different composition or volatile content. These photometric variations provide constraints on nucleus shape and surface properties that indicate an elongated object with distinct hemispheres exhibiting different responses to intense solar illumination. Radio interferometry observations detect molecular line emission from species that require high-temperature conditions for efficient production, providing evidence that thermal processing does occur despite the overall suppressed activity levels. Hydrogen cyanide and methanol lines, barely detectable during the visitor's approach phase, strengthen significantly at perihelion as solar heating liberates these species from refractory binding sites within the nucleus structure. The appearance of these high-temperature traces confirms that surface regions do achieve temperatures sufficient for vigorous sublimation, even though the overall gas production remains mysteriously restrained. High-velocity spectroscopy reveals gas expansion patterns in the inner coma that differ systematically from those observed in typical comets at similar solar distances. Water vapor velocities remain lower than expected for the intense heating conditions present at perihelion, while carbon monoxide exhibits velocity distributions that suggest multiple temperature components within the expanding gas cloud. These kinematic signatures indicate complex thermal conditions within the nucleus where different volatile species respond to solar heating according to different physical mechanisms, possibly reflecting the heterogeneous composition and structure that characterize interstellar objects. The dust tail morphology undergoes subtle changes during perihelion passage as radiation pressure effects intensify under the enhanced solar photon flux. Smaller particles experience stronger acceleration away from the nucleus, creating enhanced separation between different size populations within the tail structure. Yet the overall dust production remains insufficient to create the dramatic tail development typical of bright comets at perihelion, resulting in tail structures that appear more diffuse and less well-defined than expected for objects receiving such intense solar heating. Thermal modeling suggests that the visitor's perihelion behavior results from the combination of its exotic composition, unusual thermal properties, and the protective lag deposit that developed during the approach phase. The organic-rich surface layer acts as thermal insulation that prevents efficient heat transfer to subsurface ice reservoirs, while the enhanced refractory content of interstellar material creates sublimation physics that operate according to different rules than those governing solar system objects. These factors combine to produce a comet that can survive intense solar heating without exhibiting the dramatic activity increases that characterize native objects under similar conditions. The Perihelion passage provides unprecedented opportunities for detailed observations of an interstellar object under extreme heating conditions. Yet the visitor's muted response creates as many questions as answers about the physics of material formed in distant stellar environments. The combination of exotic chemistry, unusual thermal behavior, and sophisticated protective mechanisms demonstrates the diversity of physical processes that can operate in objects formed under conditions vastly different from those in our solar system. Each measurement obtained during this brief but intense phase of the visitor's solar encounter contributes crucial data for understanding how interstellar material responds to stellar radiation and how planetary formation processes may operate differently in other stellar systems throughout the galaxy. The mysterious restraint that characterizes the visitor's perihelion passage will influence its entire subsequent evolution as it departs the inner solar system, carrying surface modifications and internal thermal changes that reflect its encounter with our star's intense radiation. The exotic interstellar material that survived millions of years of galactic wandering now bears the permanent signature of solar system processing, creating a hybrid object that combines interstellar origins with solar heating effects in proportions that will remain forever altered by this brief but significant encounter with our Sun. Solar wind pressure, streaming outward from our star at velocities approaching 400 kilometers per second, encounters the escaping gas and dust from the visitor's nucleus with forces that sculpt one of nature's most elegant phenomena, the cometary tail that transforms a localized source of activity into a structure extending millions of kilometers across space. At perihelion distance, where solar wind particle densities reach maximum values and magnetic field strengths intensify dramatically. These plasma interactions create tail formation processes that operate with efficiency enhanced by the proximity to our Sun's corona and the acceleration regions where solar wind achieves its terminal velocity. The ion tail develops first, formed from electrically charged atoms and molecules created when solar ultraviolet radiation strips electrons from neutral gas escaping the nucleus. Carbon monoxide ions, abundant in the visitor's exotic composition, respond immediately to electromagnetic forces in the solar wind magnetic field, accelerating to velocities that can exceed 100 kilometers per second within hours of their creation. These CO+ ions, glowing blue through fluorescence processes that convert solar ultraviolet energy into visible light, create a straight tail structure that points directly away from the Sun regardless of the comet's orbital motion through space. The physics governing ion tail formation operates through magnetic field line reconnection and plasma acceleration mechanisms identical to those responsible for auroral phenomena in planetary atmospheres throughout the solar system. Solar wind magnetic field lines, stretched and twisted by their interaction with the comet's plasma environment, accelerate cometary ions along field-aligned trajectories that create the characteristic straight-line geometry observed in ion tails. The blue coloration characteristic of carbon monoxide ion emission distinguishes the visitor's ion tail from typical comets, where water group ions create different spectroscopic signatures through their distinct electronic transition probabilities. The dust tail forms through entirely different physical processes, as solar radiation pressure acts directly on solid particles escaping from the nucleus surface. Photons from the Sun carry momentum that transfers to dust grains through absorption and scattering interactions, creating forces that can overcome the weak gravitational attraction of the comet nucleus for particles smaller than several micrometers in diameter. Unlike ion tail particles, which travel at velocities determined by electromagnetic acceleration, dust grains follow ballistic trajectories governed by the balance between solar radiation pressure, solar gravity, and the initial velocity imparted by escaping gases. The visitor's dust tail exhibits a curved geometry that maps its orbital motion through space as particles of different sizes respond to radiation pressure with varying degrees of acceleration. Smaller grains, with higher surface area to mass ratios, experience stronger radiation pressure and separate more rapidly from the nucleus orbital path, while larger particles remain more closely coupled to the comet's gravitational influence. This size-dependent sorting creates a tail structure that spreads in both spatial extent and particle size distribution, with the smallest grains forming the most curved portion of the tail and the largest particles remaining close to the nucleus orbital trajectory. High-resolution imaging resolves fine structure within both tail components that reveals the complex dynamics operating in the visitor's plasma and dust environments. The ion tail exhibits narrow streamers and knots of enhanced brightness that trace magnetic field configurations and plasma instabilities in the solar-wind interaction region. These structures, evolving on timescales of hours to days, provide insights into magnetohydrodynamic processes that operate throughout the solar system, wherever stellar winds encounter planetary or cometary atmospheres. Spectropolarimetry observations reveal that dust particles in the tail scatter sunlight with polarization signatures that encode information about grain shapes, sizes, and compositions inherited from the visitor's interstellar formation environment. The degree of linear polarization varies systematically with position in the tail, reflecting the sorting processes that segregate particles according to their physical properties. Measurements of polarization angle variations provide constraints on magnetic field orientations in the tail plasma and the alignment mechanisms that can orient spherical dust grains in electromagnetic fields. The tail's optical properties evolve continuously as new material escapes from the nucleus and older particles disperse throughout the inner solar system. Color measurements reveal wavelength-dependent scattering that reflects both the intrinsic properties of interstellar dust and the effects of solar heating during the particle's journey through the tail structure. Ultraviolet observations detect fluorescence from organic compounds coating dust grains, while infrared measurements probe thermal emission from particles heated to temperatures determined by their size and heliocentric distance. Radio observations detect synchrotron emission from relativistic electrons accelerated in the visitor's magnetosphere, providing evidence for plasma acceleration processes that operate at energies exceeding those typically observed in cometary environments. These high-energy particles, possibly accelerated through magnetic reconnection events in the bow shock region, create radio signatures that serve as remote probes of plasma physics operating under the extreme conditions present during close solar encounters. The synchrotron emission exhibits polarization characteristics that trace magnetic field geometries and particle acceleration mechanisms throughout the visitor's plasma environment. The dust tail's thermal properties reveal systematic temperature variations that reflect both solar heating and radiative cooling processes operating on particles throughout the tail structure. Infrared thermal emission measurements detect temperature gradients that depend on particle size, composition, and heliocentric distance in ways that provide constraints on the thermal properties of interstellar dust exposed to intense solar radiation. These temperature measurements reveal thermal conductivity and heat capacity values that reflect the exotic compositions and structural properties acquired during the visitor's galactic wandering. Meteoroid impact detectors on spacecraft throughout the inner solar system begin to register encounters with dust particles shed from the visitor's tail, providing direct samples of interstellar material for laboratory analysis. These microscopic fragments, traveling at velocities determined by their ejection from the comet and subsequent orbital evolution, carry isotopic and mineralogical signatures that preserve direct evidence of stellar nucleosynthesis and interstellar processing from regions of the galaxy beyond the reach of traditional astronomical observations. The ion tail's spectroscopic properties reveal plasma temperature and density conditions that operate under the extreme solar wind environment present during perihelion passage. Electron temperatures, determined through analysis of emission line ratios, reach values exceeding 10,000 Kelvin as solar wind heating and magnetic reconnection processes energize the cometary plasma. These temperature measurements provide insights into thermodynamic processes that operate in plasma environments throughout the solar system and in stellar wind interaction regions around other stars. Magnetic field measurements reveal the complex three-dimensional structure of the visitor's magnetosphere as it responds to variations in solar wind pressure and interplanetary magnetic field orientation during perihelion passage. The bow shock that forms upstream from the comet exhibits dynamic behavior that reflects the changing balance between gas production from the nucleus and solar wind momentum flux. These magnetospheric observations provide insights into plasma physics processes that operate throughout the solar system and in analogous stellar wind environments around other stars throughout the galaxy. The tail formation process demonstrates the fundamental role of stellar radiation and particle emission in shaping the evolution of small bodies throughout planetary systems. The visitor's exotic composition creates tail structures with properties that distinguish them from all previously observed cometary phenomena. Yet, the underlying physics operates according to universal principles that govern similar processes around other stars throughout the galaxy. As the ancient interstellar wanderer unfurls its temporary monument across millions of kilometers of space, it creates a transient but spectacular demonstration of the forces that shape matter in motion throughout the cosmos, revealing how stellar energy can transform invisible wanderers into visible beacons that bridge the gap between worlds and stars. The tail's gentle unfurling proceeds with mathematical elegance as each escaping particle follows trajectories governed by celestial mechanics, principles that operate identically throughout the universe. Dust grains, liberated from ice matrices that formed around other stars, now trace parabolic paths through our solar system under the influence of our sun's radiation pressure and gravitational field. These particles, carrying within their crystalline structures the chemical signatures of stellar nucleosynthesis from distant regions of the galaxy, create temporary streamers that will persist for months after the visitor's departure, gradually dispersing throughout the inner solar system to join the population of interplanetary dust that connects all planetary bodies in our stellar neighborhood. The ion tail reaches its maximum development during perihelion passage as gas production rates plateau at levels sufficient to create substantial plasma densities throughout the visitor's magnetosphere. Carbon monoxide ions, accelerated to relativistic velocities through magnetic field interactions, stream away from the comet along field lines that extend beyond the orbit of Mars, creating a blue-tinted beacon visible through modest telescopes from Earth's surface. This plasma structure, fed by sublimation of ice that condensed in stellar formation regions light years from our Sun, demonstrates the fundamental connection between stellar evolution processes and the dynamic phenomena observable throughout planetary systems. The electromagnetic signatures of tail formation provide insights into plasma physics processes that operate on scales ranging from individual particle interactions to magnetohydrodynamic waves that propagate throughout the heliosphere. Electric field measurements reveal charge separation processes that create potential differences exceeding millions of volts between different regions of the tail structure, while magnetic field observations detect alpha waves and other magnetohydrodynamic phenomena that transport energy and momentum throughout the visitor's plasma environment. These measurements contribute to understanding of space plasma physics that applies to stellar wind interactions throughout the galaxy and in the magnetospheres of exoplanets orbiting other stars. As the visitor's tail reaches its full magnificence during the brief perihelion passage, this temporary structure serves as a cosmic laboratory that reveals the fundamental processes governing matter and energy throughout the universe. The ancient material that preserved interstellar conditions for millions of years now creates a spectacular display that demonstrates how stellar radiation can transform wandering debris into one of nature's most elegant phenomena. Connecting our solar system to the broader galactic environment through the universal language of physics that governs the motion of matter throughout space and time. The departure begins imperceptibly, marked not by dramatic changes visible to casual observers, but by subtle shifts in orbital velocity and plasma interactions that signal the visitor's gradual withdrawal from our Sun's intense influence. Having survived perihelion passage with its mysterious restraint intact, the ancient wanderer now follows hyperbolic trajectories that carry it away from the inner solar system along paths governed by the same gravitational mechanics that brought it inward, yet modified by the accumulated effects of solar heating, outgassing forces, and the subtle rocket accelerations that have altered its departure velocity by measurable amounts. Solar heating diminishes with mathematical precision as distance from the Sun increases beyond 1 astronomical unit, following inverse square relationships that govern radiative energy transfer throughout the universe. Surface temperatures that reached 500 Kelvin during perihelion gradually decline toward values that will eventually match the cosmic background radiation temperature of deep space. Yet the thermal inertia of the nucleus interior creates temperature gradients that persist long after surface cooling begins, maintaining sublimation activity at levels that continue to feed gas and dust production for months following closest solar approach. The visitor's activity patterns evolve systematically as changing thermal conditions alter the balance between different sublimation processes operating throughout the nucleus structure. Water ice production, suppressed during the strange pause and muted even at perihelion, begins a gradual decline that follows exponential relationships determined by the temperature dependence of vapor pressure curves. Carbon monoxide sublimation, less sensitive to temperature variations due to its lower binding energy, maintains relatively constant production rates that create evolving compositional ratios in the escaping gas as the comet recedes from peak heating conditions. Spectroscopic observations detect systematic changes in emission line intensities that trace the thermal evolution of different regions within the nucleus as conducted heat from perihelion passage continues to migrate inward toward the visitor's core. Temperature-sensitive molecular transitions reveal cooling patterns that encode information about thermal diffusivity and internal structure throughout the nucleus interior. These measurements provide constraints on the three-dimensional temperature distribution and the thermal properties that distinguish interstellar material from objects formed within our solar system. The plasma environment surrounding the visitor undergoes progressive changes as gas production rates decline and solar wind pressure decreases with increasing heliocentric distance. The bow shock that formed during perihelion passage gradually weakens and eventually disappears as escaping gas densities fall below thresholds required to deflect the solar wind. Magnetometer measurements detect the transition from active plasma interactions to passive solar wind flow around an essentially neutral object, marking the visitor's transformation from active comet back toward the inactive state that characterized its approach through the outer solar system. Tail morphology exhibits systematic evolution as radiation pressure effects weaken with increasing solar distance and gas production rates decline toward levels insufficient to maintain vigorous dust emission. The ion tail, fed by decreasing ionization rates as solar ultraviolet flux diminishes, gradually fades from visibility as electromagnetic acceleration becomes insufficient to maintain the high-velocity plasma streams that created its characteristic straight-line structure. The dust tail persists longer due to the ballistic nature of particle motion, but gradually disperses as new dust production decreases and existing particles follow independent orbital trajectories determined by their size-dependent response to radiation pressure. High-resolution imaging reveals that the nucleus surface continues to evolve even as overall activity levels decline, with thermal expansion and contraction cycles creating ongoing modification of surface features and volatile distribution patterns. The protective lag deposit that developed during the approach phase undergoes restructuring as thermal cycling creates fractures and exposes fresh ice in localized regions. These surface changes, operating on timescales of days to weeks, create episodic variations in gas production that persist long after the systematic decline predicted by simple thermal models. Radio interferometry observations detect the gradual disappearance of molecular line emission as gas densities in the coma fall below detection thresholds for ground-based instruments. The exotic carbon monoxide signature that distinguished the visitor throughout its passage maintains visibility longer than typical water-dominated cometry spectra due to CO's efficient excitation at low densities, but eventually fades below instrumental sensitivity as expansion velocities carry molecules beyond the beam sizes of terrestrial radio telescopes. Infrared. Thermal measurements reveal that surface cooling proceeds more slowly than expected based on simple radiative equilibrium models, indicating that the organic-rich lag deposit continues to influence thermal transport even during the departure phase. The insulating properties that created the mysterious activity suppression during approach now delay surface cooling and create temperature profiles that maintain elevated interior temperatures long after perihelion passage. These thermal effects will influence the visitor's appearance and activity levels throughout its journey back toward the outer solar system. The dust tail begins to exhibit structural changes as different particle populations respond to varying degrees of radiation pressure acceleration with increasing heliocentric distance. Larger grains, less affected by radiation pressure, gradually separate from smaller particles that continue to experience significant acceleration away from the Sun. This evolutionary sorting creates systematic changes in tail brightness, distribution, and optical properties that encode information about particle size distributions and the physical processes that control dust production during the active phase of the visitor's solar encounter. Plasma physics measurements detect the gradual decay of electromagnetic phenomena as decreasing gas production reduces the charged particle densities that drive magnetic field interactions and plasma wave generation. Synchrotron emission from relativistic electrons accelerated during perihelion passage fades as particle acceleration mechanisms become less efficient in the weakening plasma environment. These changes mark the visitor's transition from an electromagnetically active object back toward the neutral state that will characterize its eventual return to interstellar space. Ground-based photometry reveals that brightness decline follows power law relationships that differ systematically from those observed in solar system comets, reflecting the exotic composition and thermal properties that distinguish interstellar objects from native solar system materials. The visitor's light curve exhibits irregular variations superimposed on the overall decline, possibly reflecting heterogeneous surface properties and the complex thermal evolution of different regions across the nucleus as cooling progresses at different rates depending on local composition and structure. Astrometric observations detect continuing perturbations in the visitor's trajectory as outgassing forces maintain non-gravitational accelerations that accumulate over time to produce measurable changes in orbital parameters. The rocket effect that created systematic deceleration during approach now operates under different thermal conditions, creating force vectors that depend on the evolving pattern of gas production as surface cooling alters sublimation distributions across the rotating nucleus. These trajectory modifications will ultimately change the visitor's departure velocity from the solar system and alter its future galactic wandering path. The visitor's gradual retreat from the inner solar system proceeds with the same patient inevitability that characterized its initial approach. Yet now it carries within its modified structure the permanent signatures of solar heating and the accumulated effects of our star's radiation on material formed around other stars. Surface chemistry altered by thermal processing, internal temperature gradients established during perihelion passage, and the evolved lag deposit created through sublimation processes will accompany the visitor throughout its future journey across interstellar distances, creating a hybrid object that combines interstellar origins with solar system processing in proportions that record the details of this brief but significant encounter with our Sun. The hyperbolic farewell unfolds across astronomical scales as the visitor's trajectory curves away from our Sun, along paths that will carry it beyond the gravitational reach of any solar system object and back into the galactic wilderness from which it emerged. At distances exceeding 2 astronomical units, where solar heating becomes insufficient to drive significant sublimation activity, the ancient wanderer begins its transformation back toward the inactive state that characterized millions of years of interstellar drifting. Yet the thermal signatures of its solar encounter will persist for decades as conducted heat continues to migrate through the nucleus interior, creating temperature gradients that preserve memories of perihelion passage long after surface cooling reaches equilibrium with the cosmic background radiation. The mathematics of orbital mechanics dictates that objects following hyperbolic trajectories must eventually escape any bound gravitational system, carrying excess kinetic energy that prevents capture into periodic orbits around the central star. The visitor's departure velocity, modified by the cumulative effects of outgassing forces and gravitational interactions with planets throughout the solar system, will ultimately determine its future motion through the galaxy and the stellar systems it may encounter during subsequent epochs of cosmic time. Computer simulations suggest departure speeds approaching 40 kilometers per second relative to the Sun, velocities that will carry the visitor across interstellar distances measured in light years over time scales of millions of years. Surface temperatures continue their systematic decline as solar flux diminishes according to inverse square law relationships that govern radiative energy transfer throughout the universe. At 3 astronomical units from the Sun, surface temperatures approach 200 Kelvin, still warm enough to sublime carbon dioxide and other volatile species, but insufficient to maintain the vigorous water-ice sublimation that characterizes comets in the inner solar system. The visitor's exotic composition creates sublimation cascades that operate in reverse as cooling progresses, with the most volatile compounds ceasing production first, while more refractory species maintain activity to greater solar distances. The plasma environment that surrounded the visitor during its active phase gradually dissipates as gas production rates fall below levels required to create substantial ion densities in the solar-wind interaction region. Magnetometer measurements detect the final disappearance of bow-shock structures and magnetic field perturbations that marked the visitor's presence as an electromagnetically active object. The transition back to passive interaction with the interplanetary medium occurs gradually over weeks and months, reflecting the thermal inertia of nuclear heating processes and the exponential dependence of sublimation rates on temperature. Spectroscopic observations reveal the systematic disappearance of emission lines characteristic of different molecular species as gas densities fall below detection thresholds for ground-based instruments. Carbon monoxide signals, which dominated the visitor's spectrum throughout its solar system passage, fade more gradually than water vapor emissions due to CO's enhanced production efficiency at low temperatures and its distinctive excitation properties in low-density environments. The final detection of cometary emission lines marks the end of direct chemical analysis of interstellar material under solar heating conditions, concluding unprecedented opportunities to study exotic compositions through remote sensing techniques. The dust tail begins its gradual dispersal throughout the inner solar system as radiation pressure continues to accelerate particles along trajectories that will eventually carry them throughout interplanetary space. Larger grains, following ballistic paths determined primarily by gravitational forces, remain gravitationally bound to the solar system and will eventually settle into heliocentric orbits that contribute to the population